want to do is finish up from the cliffhanger where we started left off last time, which is how we can find a unit sample response for a system. And we looked at one method last time, which was we could always do that. We could always find sample values of the unit sample sequence, just like we can find the sample values of any output sequence for a given input by using recursion, the little table method. And in that case, we would put in a delta then sequence, a single 1 at n equals 0, and let it propagate through. And the values of whatever came out would be, by definition, the unit sample response, because we put in a unit sample sequence as an input, as long as we started with initial conditions being 0. Now, so we did that for a couple cases, and we saw that some filters, non-recursive filters, have a finite length impulse or unit sample sequence, a finite number of non-zero samples, and that actually we could pick off those sample values from these B coefficients in the difference equation, so those are easy to find. Recursive systems, though, tended to have infinite impulse response or infinitely long unit sample sequences, and so while recursion will give us a bunch of great sample values, it won't give us a closed form solution, an analytical expression for the unit sample response. If we want to find that, we've got to solve the difference equation, for the right set of conditions for a relaxed system for a unit sample sequence input. And what we'll see today is, well, that's all well and good, but we've got to actually kind of tweak the process a little bit, because this unit sample sequence is pretty unique. It's just got a single non-zero sample that's happening right at n equals 0, and so after that it's always 0, and so it kind of messes up my finding of a forced response. So we're going to have to modify the way we handle that. So that's what we'll do today. We'll look at how to do that, how to solve the difference equation to find the unit sample response of a system. And then we'll look at what else can we tell about the system and its characteristics by looking at the unit sample sequence. Turns out we'll be able to tell whether the system's causal or non-causal, whether it's stable or unstable from the unit sample sequence. So we'll cover all that, and then if a little time left over, we'll go through one part of another difference equation solution method to get a little bit more practice on that before we move on to convolution and parts unknown on Friday. So that's where we're heading today. So how do we do this? Well, you give me a general case difference equation and ask me for the unit sample response, and if it's recursive, then it's going to be a little bit of a challenge. What we'll do, though, is treat the unit sample sequence like a zero-state response, which it is, because we're starting with the assumption that the initial conditions are 0. Now, maybe that's not obviously why we're doing that. We're going to do that because we want to use this unit sample sequence to generalize the response of the system to any particular input. If that being the case, I can't have any initial condition stuff messing up my unit sample sequence. So we're working with the assumption that we're talking about the response of a relaxed system to a unit sample input. That's what we're calling our unit sample response h of n. Because it's a zero-state response, we can't solve the general one right away. We have to demote the difference equation to a single input case. So we throw away everything on the right-hand side, replace it with x of n, which in this case happens to be a unit sample sequence, delta of n. And in our notation here, I just replaced the y's with h of 0. Only to remind us that, well, h of n, because we're finding a unit sample response, the 0 is reminding me, well, we're in the single input case, we're not in the general case. Okay, so that's the nomenclature there. So we still do that. We still go to a single input case and solve that. Now, we do this in a special way. Instead of what you might expect in our standard process, we would solve the single input case zero-state response for a unit sample sequence input and 0 initial conditions. Instead of that, we set the input equal to 0 and use a special initial condition that the unit sample sequence output at unit sample response sequence output at n equals 0, we set equal to 1. standard initial conditions, we keep it 0 because it's still a 0 state response. But we set this up, and what we're doing here effectively is the same kind of thing we were doing in continuous time systems. My unit sample sequence input doesn't really work with my solution method because from a forcing function standpoint of view, it goes away at n greater than 0. So I can't call it a constant. I can't call it an exponential. I don't know what to do with it. So instead of that, we say, well, there's no input. And we let the effect of that 1 and n equals 0 show up here as part of that initial condition that we're going to solve for. And so, as we'll see, it actually works for us. But that's the way we have to tweak the process when we're using this unusual unit sample sequence input. The rest of the process goes along the same. There's no 0 input response because it's a relaxed system. If I assume my input is 0, there's no forced response either. Okay. Which means what am I left with? Usually we would say a 0 state response, even a single input case one, as a forced response piece and a natural response piece, right? If I tell you the input is 0, there's no forced response. So by definition, the unit sample sequence, the unit sample response, is going to have the same shape as a natural response, and only the natural response. Well, that's actually kind of good news for us because we're going to use this input in convolution to tell us what's the response of the system to any input. So I don't think I want in my general function anything that feels like a forced response to a particular input. But I definitely want to know how is the system going to naturally respond? What's its transient response shape going to look like? So I better get the same shape as the natural response in my unit sample response. And in fact, we do. So let's try one. Well, after you do that, we find the unit sample sequence, the unit sample response, I'm sorry, for the single input case, and then just like we would for any 0 state response, we promote it to the general solution by applying all the multiplication and delay operations of the general difference equation, the right-hand side, to that unit sample sequence single input case result, just like we would for any 0 state response. Okay? That sounds kind of confusing, so let's do an example. Let's take our system that we solved before and find the unit sample response of our favorite difference equation there. And we already have derived, we ran that difference equation into a recursion table, and so we already know what the answer is supposed to be, at least what some sample values are, right? I think it was a 1, then a 1/2 maybe, and a -1/4, and let's get a marker that marks. -1/4, and then +1/8, and -1/16, so on and so on. If you look back in your notes, I think that's what we got. So whatever closed form solution we come up with better produce those results. Let's see if we can do that. All right. So this is a general difference equation. I've got multiple x terms on this side, so we're trying to find the unit sample sequence. So we'll start with a single input case. Which means now we're solving for H0 then the single input case, unit sample sequence, turn our equation around +1/2, H0 of n -1 equals x of n, which also happens to be a unit, well, let's keep it x. That's the equation we're solving for. We want to find H0 of n so that we can promote it up to the general H of n. And And normally we'd find a forced response because we know this is going to be some forced response and some natural response. But since our x sub n in our new model is 0, that's our new special way of handling this particular case. If there's no input, then there's no force response. So all I'm left with is this natural response piece. We've already solved the characteristic equation for this system. We saw the characteristic equation was z plus 1/2 equals 0, so z equals minus 1/2, right? Excuse me, from the difference equation. So our natural response piece is going to be some unknown k times minus 1/2 to the n. And the initial condition we're going to use is a special one, h0 of n equals 0. That's a 0. Equals 1. And that was the other part of our special way of dealing with finding the unit sample sequence. Using an initial condition at 0, not minus 1, and we set it equal to 1 for the single input case. And so if we plug in n equals 0 into this expression, that's a k times minus 1/2 to the 0, which is just k. That has to be equal to 1, so k must be 1. So our h0 of n equals just 1 times minus 1/2 to the n. And like u of n, n greater than 0. Everybody okay with what we did? So again, things was different. We said x sub n was 0, so that was part of our model. So there was no forced response. Now, even though this is technically a 0 state response, I'm using an initial condition of 1 at n equals 0. The initial conditions of minus 1, minus 2, those are still 0. Yeah?
What is it on the force response portion? What does that say right next to the x of n? It's like S-I-N-A, or I can't read that.
This one?
Yeah. Oh, since. I'm sorry, I thought it was something else.
You thought it was something interesting.
Yeah.
Yes, keep me honest. This is a 1, not a 2. Okay, so everybody see how we got there? All right, that's still the single input case. We want to go up to the general case. Our general unit sample sequence, well, let's got to look at what's going on in our difference equation. I have an x of n on this side. I also have an x of n minus 1. So the 0 state responses generalize by starting with the original unit sample sequence because of the x of n there, and a delayed version of it because of this x of n minus 1 term. And again, if I had some multiplier out here, like a 3 in front of that, I would have put a 3 in front of this as well. So every operation with the right side of the difference equation starts to do the x of n, multiply it, delay it, all those get done to the 0 state responses. Well, that's easy. We know h of 0 n, that is a minus 1/2 to the n, u of n, and a delayed version of that is minus 1/2 to the n minus 1 power, u of n minus 1, delayed unit step. And we have the total unit sample response of our system. Now if I plug in, so this was n equals 0, 1, 2, 3, yeah. If I plug in n equals 0 into that formula, I better get a 1. So that's minus 1/2 to the 0 power. U of n at n equals 0, what value does that have? Looks like this, right? That's our U of n. Should be the same level, I'll put 1. So at n equals 0, U of n has a value of 1. And I add minus 1/2 to the n minus 1, that's minus 1, times U of n minus 1. That looks like that's a delayed version. So this would be a U of minus 1. Pretend that's going to be 0. And we just get, looks like 1. And similarly, your h of minus, or h of plus 1, plug in n equals plus 1 into this, get minus 1/2 to the first, times U of n is 1, plus minus 1/2 to the 0, and U of n minus 1 at n equals 1 is going to give me a 1. So I think we pick up a minus 1/2 there, we pick up the plus 1, which is plus 1/2, which is what we got there, and so on. So this expression we came up with is an analytical form for that gives these same sample values that we got by the recursion table. And that's it. That's the whole method. So we're still solving a difference equation. We're just kind of tweaking the process a little for this special case of finding a unit sample sequence. How we doing? Questions? Makes sense? It's a little weird, but works. It matches up with our results before. That's comforting. Okay. That's Sue. So our unit sample, that unit sample sequence, 1/2 to the n minus 1/2 to the n minus 1. Again, we saw it was a 1, 1/2, minus a quarter, plus an eighth, oscillating back and forth. It's decaying, never quite getting to 0. We would have called this an infinite impulse response filter. This one never quite gets to 0, so it's definitely an IIR system. And it was recursive, we saw that. So it seems to be fitting in with our expectations. Okay. That's how we find unit sample sequences. Now what can we do with them? Well, the big thing we want to do with it is convolve it with something. But we're not ready to do that yet. Before we do that, we can actually make use of the unit sample sequence, if we found it, to tell whether our system is stable or not, or causal or not. How are we going to do that? Well, first, for stability, we start with the simplest definition, just like we did in continuous time systems. That was, if I put any bounded input signal, any bounded discrete time signal in, what comes out better also be a bounded output signal. It's bounded input, bounded output, BIBO stable. Which makes a lovely definition, but it's kind of hard to use that as a test for whether a system is stable or not, because if I wanted to prove it with this definition, I would have to apply every possible bounded input signal and make sure I didn't get an unbounded output. I don't have enough time left in my life to do that, so we're going to have to find something better. Mathematically, we would express this requirement as x of n being bounded, meaning if I take the absolute value of all the sample values of x for any value of n, all of those better be some finite value, less than n, where n can't be infinity. And same definition for the output, y of n has to also be bounded, meaning its absolute value has to be a finite value as well. It could be bigger than the input, that's all right, as long as it's not infinite at any point. lovely, makes the mathematicians happy. Excuse me, doesn't make us engineers very happy because I can't use that as a definition. Turns out, just like we could tell whether a system's linear or nonlinear, time invariant or time varying from the difference equation, we can tell whether it's stable or not from the difference equation in a way that actually makes sense if you think about it. Here's how we do it. If you're looking at the difference equation, well, you got to go a little bit beyond that. You got to find the characteristic equation, find the roots of the characteristic equation, and check them and make sure all of them have magnitudes less than 1. And where's our natural response? We have, there's our natural response. So remember, when we're creating a natural response, we look up, we take that root of the characteristic equation, and we raise it to the n power. Kind of makes sense that the thing I'm going to raise to a power better be a number less than 1. Because if it's bigger than 1, if it's like 2, 2 to the n is going 2, 4, 6, no, excuse me, 2, 4, 8, 16. It's exponentially growing. If this number is a fraction, then it's going to be decaying exponentially. So essentially, this is a fancy way of saying your system better have a decaying kind of a converging kind of natural response. And it will if all roots of my characteristic equation have magnitudes less than 1. And we say magnitude because they're not always real roots like this. Sometimes we have complex roots. That's all right. This means if you look up in the table, that means you have maybe a sine or cosine. If its magnitude though is less than 1, it's going to be a converging function again. So, and we'll look at one of those examples at the end. But this requirement constrains us to have a natural response that's a converging function. So if you extracted your characteristic equation from the difference equation and had one like this, c squared plus z plus a quarter equals 0. You solve for the roots, you found, oh, I've got repeated roots. These are okay, even though they're repeated, that's fine. We get 1/4 to the, minus 1/4 to the n. Out of that, they have magnitudes less than 1, so this is going to be a converging function. Even though, remember, the natural response is going to be some k times 1/4 to the n, and because of repeated roots, I'm going to have an n times. That's a little scary to me, because I have an n that is growing with n, as n increases, right? But it turns out this fractional value, this 1/4 of the n, is going to converge faster than this diverges. It's going to keep it forced to keep it under control. So this is fine. Repeated roots, as long as all the roots have magnitudes less than 1. Here's one where the roots aren't that way. You have this characteristic equation. You have 2 real roots, but they're both have magnitudes greater than 1. They'll produce natural responses like 2 to the n and minus 4 to the n. So they're going to be growing, 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 growing. Those would be an unstable system. This one's a little trickier. This one has roots of positive 1 and minus a quarter. Well, the minus a quarter is okay. I get a minus 1/4 of the n, that's converging. The 1 is a constant. 1 to the n just stays constant, 1 constant, 1 constant, 1 constant, 1. That one you might think that's okay. It's not unstable, right? It's not going anywhere, it's not growing. So like if you look at its unit sample response, put in a 1, and it just stays level. That looks like it might be stable. But again, if I can find any bounded input that makes it go off to infinity, then it fails. And it turns out it's pretty easy to. If I put in the unit step function, and looks like we get a bounded output or bounded input. But I put a unit step in, off it goes. Now, why? Let's see if we can figure out why that would be. Let's back up. So I had 2 roots. I have a natural response. It looks like, I don't know what we got, k0 times 1 to the n, and a k1 times minus 1/4 to the n. And these are u of n's if you like. Nothing wrong with that. Well, what happens if I come along and say my x of n equals 1 for n greater than 0, which is the same as it's a unit step. Then technically, my forcing function is the same as a root of the characteristic equation, right? And we have a special case solution of the difference equation, which means my input, my force response, then is not a constant anymore, but what is it? Times n. So the force response piece is going to give me that growing, come on, that growing with n force response. Right? See, you knew enough to understand that even. Okay, so this is an unstable system. And what that says is the borderline condition, the marginal condition, the equals to 1 doesn't work. It has to be less than 1. Okay? If you're looking at unit sample responses, there's also a way to tell whether the system is stable or not. That is, the values, the sample values in the unit sample sequence h of n have to be absolutely summable. What does that mean? That means I have to be able to take the absolute value of all the samples of h of n, add them all up, and get a finite value. So it doesn't help me if I'm oscillating positive, negative. Make them all positive, add them all up, and if I get infinity, I'm in trouble. If I get anything less than infinity, it's okay. And so if I have, for example, an FIR system, finite impulse response system, that has only like, say, 5 non-zero values of h of n, sample values, it's going to be stable, right? Have a finite length unit sample response, its sum is going to be finite. So that's one really beautiful thing about FIR systems. H of n is always absolutely summable, which means they are always, 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 always stable. That's really nice. You can design a discrete time system that you don't have to worry about stability. It's just rock solid, gonna be stable forever. That's an FIR system. You can only design them in discrete time systems. You don't have a continuous time equivalent of them. It's a neat new thing we have available to us in discrete time systems. So this one, this was our unit sample response for that case we were looking at, where I get a constant output. Well, if this is my unit sample response, my h of n, and I add up all the values of this h of n for all n, well, I'm just going to keep adding 0.8, 0.8, 0.8, 0.8, 0.8, 0.8, an infinite number of 0.8s versus infinity. So this is not an absolutely summable unit sample sequence. Therefore, it's not a stable system. Yeah, no, not absolutely summable. How about this one, our friend here? One we've been solving. It looked like it was pretty well behaved. However, its roots the characteristic equation. They were minus 1/2. That's fine. That's less than 1. Should be stable. How about this? I've got minus 1/2 to the n u of n's. Is that summable? Is that absolutely summable? So we have to ask ourselves, for stability, we want the sum over all n from n equals minus infinity to plus infinity. An absolute value of h of n has to be some finite value. Let's just say less than infinity. Well, what is, it's a causal unit sample sequence. So let's take the first half. Let's take this piece. It's minus 1/2 to the n u of n. What would that look like? That's a sum of the absolute value of 1/2 to the n. So an absolute value of minus 1/2 to the n from n equals, starts at 0, it's causal, plus infinity. That's like a sum from n equals 0 to infinity. Don't need that minus sign. 1/2 to the n. Anybody know what that sum is? Anybody remember your series summation formulas? Power series, k equals 0 to infinity of alpha to the k. 1/1 minus alpha. As long as the magnitude of alpha is less than 1. It's a converging series. So it turns out this converges to 2. And similarly, this one is just this delayed by 1. So, okay, you're going to pick up most of another 2. So it's definitely going to be a finite summation. Okay? So h of n tells us that it's a stable system. The difference equation tells us that it's a stable system. Probably easier to get it from the difference equation. But if you got just h of n, you don't have a difference equation, you can find it with that. All right? For causality, there's a nice simple test for causality of a unit sample sequence. For a causal system, its unit sample sequence h of n has to be 0, 0, 0, for any value of n less than 0. Or in shorthand, which is just a mathematical way of saying you're not allowed to respond, h of n can't be anything other than 0, until after the input arrives. Input arrives at n equals 0. So if we're putting in a unit sample sequence, the unit sample response better not start any sooner than I put the 1 in. And if my unit sample sequence is a 1 at n equals 0, that means all the negative values of n better have sequence values of 0 in my unit sample sequence. If any of them is non-zero, if I get something out here, then I responded before I got hit. That's an anticipating system. That's not a causal system. So again, if I've got a unit sample sequence, I can look, if I have a unit sample response for a system, I can tell right off the bat if it's causal or not. Again, I can also tell from the difference equation, but this gives me an alternate way to do it. Make sense? Conceptually? So now, by looking at difference equations or unit sample sequences, unit sample responses, we can tell, well, we have to look at the difference equation to tell if it's recursive or non-recursive. We can tell if it's FIR or IIR from h of n. That's what distinguishes these. We know there's a connection here. If we have a non-recursive system, it's definitely FIR. If it's recursive, it's probably IIR, but not always, usually. Static or dynamic, we can pick that up from the difference equation. Linear or nonlinear, again, you can see that most readily from the difference equation. Time varying, time invariant. We know how to recognize that. But now we can add causal by one of 2 methods, either the difference equation or the unit sample response. And stability we can get from either of those as well. So now we've got a complete set of tools to characterize what kind of system do we have. And now we've got a set of tools for doing system analysis, finding the output for a given input in a given set of initial conditions, as long as, I don't care, gotta be linear, gotta be time invariant, I don't care. The method works even if you have a non-causal system, even if you have an unstable system, as long as it's linear and time invariant. Okay, so those are our 2 baseline requirements. The rest, okay, this tells us something about the system. In fact, in a minute, we'll break the rules a little bit and see that we actually do get a correct closed form solution. But before we do that, questions. Are we good on classification? We're good on difference equation solutions? We're good on finding unit sample sequences? You're all going to practice for homework. The quiz that you were supposed to do for today, you're going to do for Friday because I didn't post it in time. Sorry about that. I know you were terribly disappointed, but we'll handle that. Okay, any questions? Anything not doing okay? All right. In that case, let's take a slightly more interesting, slightly more complicated example just to see a little bit more about how the process works. So far for homework in our class examples, we've been using pretty trivial setups. But the real world's not that trivial. And particular we've been putting constant inputs or step inputs in, or maybe exponential inputs in. But what if we start out with a more interesting system and put in a more complicated input function? What's that going to do? And how's that going to affect the way we solve the problem? And the short answer is it's not going to change the method, just the board space is going to increase a little bit. And so with the time left, we can't go through a complete solution, but let's derive at least a zero input response, and if we have time, a forced response of this system to a cosine kind of input. This is a discrete time cosine, so it's samples of a cosine going into our system. So before we go very far, though, what can you tell me about that system? Is it linear? Brocan linear? It's got to be, or we can't go any farther. Is it shift invariant? It's okay for shift invariant. It's dynamic. Is it causal? It looks causal to me. Oh, look at this. It's even simple. And it's ish. It's a single input case. I don't have to, it's not even a general equation. I've only got x and band on one side, so I don't even have to generalize stuff. That's kind of nice. It is causal. Is it stable? What's the characteristic? Oh, come on, give me a marker, please. Is the characteristic equation of the system? I'm thinking it's z squared plus 4z plus 8 equals 0. Would you agree? Or if you can't jump that far ahead, it's a 1 plus 4z to the minus 1 plus 8z to the minus 2 equals 0, which I multiply both sides by z squared and get this one. I like it this way because I can factor it. Oh, but that one doesn't factor very easily, does it? Okay. Well, let's see. Let's find the roots. Z equals negative b plus or minus square root of b squared minus 4ac all over 2a. This is the square root of minus 16. Uh-oh, it's going to have some j's. Square root, that's 4. Blah, 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 blah. I'm thinking we got a minus 2 plus or minus j2 for the roots of the characteristic equation. Complex roots. Does that scare me? Nah. Complex roots. We got that handled. We're in the table here somewhere. Where's our handy dandy table? Give me a pretty handy dandy table. Where are you? Where are you? There it is. Ah, there it is. Nope, wrong one. That one. There it is. Okay. If I have complex conjugate roots, oh, I need magnitude and phase version. Z equals magnitude, that's 2 times the square root of 2 angled at, I'm guessing, plus or minus 3 pi over 4. Or if you like in that notation, 2 square root of 2, e squared 2, e to the j plus or minus j 3 pi over 4 is what the polar form of that complex value is. Is that a stable system? Does the fact that it has complex roots make it unstable? No. It could still be stable. However, it's not stable. Why not? The magnitude is greater than 1. So it's an unstable system. Now, you might think it's prudent. It's an unstable system. So what do we do with unstable systems? Throw up our hands. Say, it's unstable, I don't care. However, our lovely methods do actually work. And we can actually find a zero input response and get a valid answer using this technique, even though it's unstable. How, you ask? Well, let's see. Anyway, everybody see why we concluded it's an unstable system. Found the roots of the characteristic equation. They had a magnitude greater than 1. And so it was unstable. All right. Well, how would we approach this? Well, if we were finding a zero input response, we would say, okay, it's a natural response. Finding the form of the natural response. Using that kind of root, we go over to our table and say that kind of root, complex root, we take the magnitude, raise it to the n power with some unknown k. Oh, no, let's keep that. We're going to hold that back. It's a magnitude 2 times the square root of 2 raised to the n power multiplied by a cosine and a sine with unknown coefficients. K1 cosine of n times the angle. 3 pi over 4 times n. And K2 times the sine of the same. 3 pi over 4 times n. And that's the shape of the natural response. Now, before we even solve for the k's, what is that? Well, it's oscillating, and it's growing. Because I have something greater than 1 to the end, so it's doing this, which an unstable system is going to do. But I'll get a valid answer. I'll get a closed form solution for what this nasty thing is going to look like. The method still works. And how do we find zero state responses? Zero input responses? How do we solve those? Unknown coefficients? Just like any other old one? What's the method? What do I need? Two initial conditions. Well, 2 unknowns. I need 2 initial conditions. It's a second order system. We have 2 initial conditions. Oh, I lost them there. We're going to have to go back to the problem. Let's go to the end. Let's go to the end. Let's go to the end. Check out our initial conditions. There they are. So y of minus 1 is 0, which is 2 square root of 2 raised to the 0 power. That's easy. K1 times a cosine of the minus 1. Oh, I'm sorry, not the 0 power, the minus 1 power. Keep me honest here, folks. And this minus 1. Minus 3 pi over 4 plus K2 sine of minus 3 pi over 4. Oh, those are just constants. Oh. Angle minus 3/4 pi. I think it's like over there. Right? 4 to 5 degrees there. So I'm thinking that's a, well, 1 over square root of 2 flipped over is 1 over 2 square root of 2 out in front. K1, K1. Cosine of that's, let's see, it's going to be cosine is negative times negative, and that's square root of 2 over 2. It's a 45-degree angle, right? And K2, the sine of that angle, sine is also pointing down. It's a 45-degree angle, so the sine and cosine are the same. And I think we've got that. And you know that this combination equals 0. Our second initial condition, y minus 2 equals 1. The problem is given. We plug that in here and get 2 squared root of 2 raised to the minus 2 power times that k1 cosine of minus 2 minus 3 pi over 2 now, I think, is our angle. Because n is minus 2. Add a k2, I'll get out of the way over here. Sine of the same angle, minus 3 pi over 2. And this to the minus 2 power is that flipped over and square, which is going to be a 1 over 8. And where are we angle-wise here? Minus 3/2 pi. I think I'm over there. So that's a k1 times the cosine of that angle. Looks like 0. Plus k2 times the sine of that angle, which is 1. Now I've got two equations, two unknowns, and if you work through that, you find that k1 is minus 8 minus 8, and k2 happens to be plus 8. So our natural response, our zero input response, is one of these guys, which again is a growing exponential oscillation, but that is the closed form solution. That is what it's going to do. So the method works, even though we have an unstable system. And if we had time, and we could put in this x of n as a cosine, well, just like we would do in any case, I have to make sure that the cosine n pi doesn't match one of the roots of the characteristic equation. Cosine, but different frequency, so it's okay. So I would treat this as a plain old force response, and look up in the table, find the force response and some other cosine, sine, and solve for this question.
Did you mean to put positive 8 in for K1?
I meant to put a minus in there.
Okay.
Thank you. Keep me honest. All right, so you are armed and dangerous, ready to solve some homework problems. I'm going to add another problem to the homework set because you're getting practice in all the initial conditions, so there's no excuses on the midterm. Do take a look at those. That homework set's due Monday. Excuse me. Friday we're actually going to move on to convolution, so you've got everything you need to know to finish all of that homework assignment. And I'll have some of your previous homework assignments to get back to you Friday as well. So see you then.